So let us look into a general formulation for A, which is a binary number, minus B. Okay, and we are assuming that both A and B are represented using k bits. Okay, and remember, what is the base of this system? The base of this system is 2. Okay, so 2 is the base of binary system, number system. Only 2 values are possible, 0 and 1. Okay, and we want to have this thing computed, A minus B. Unfortunately, we do not have a subtraction circuit. We only want to do this in terms of an addition. Okay, so how can we write this in the way we have done it for the decimal, right? What we did, we expressed this minus 8 as some plus 2 minus 10, right? We knew this thing, so we did it mentally. But in this case, of course, we do not know. So it is going to be plus something minus the base raised to a power, right? So in this particular case, we can write this as A plus something. We do not know what this something is, right? There we knew because we did this calculation mentally and trying to prove that what exactly is going to be the number. We could figure it out. Here we don't know, so I'll just try to write this as some b dash. Okay, don't think that b dash is the complement of b. It's just a notation that I'm using. Okay, often we use b prime to express complement, but it's not that. It's just that we don't know what is this. Okay, and then we can always do this minus. If you remember, in the last few cases we are using 10 square or 10 cube. So base to the power, the number of bits that we are using or the number of digits that we are using. If we are using 3 digits, we are using 10 cube. If you are using 2 digits, we are using 10 square. If you are using 1 digit, we are using 10, right? So this is nothing but 2 to the power k, right? So if I just want to write this in the same format without knowing what is this b prime's value, I can always write this, right? And then back calculate what is the value of b, what is the value of b prime. Now the target we have is to realize this value of b prime. What is this b prime? We don't know. Okay, so what will this value be again? How can this be simplified? We can write this as A. I'll come to the details why I am writing it in this format, plus b prime as it is, minus, say, 2 to the power k minus 1. Okay, minus 1. Just a different way of writing, right? I'll come to the details of why we are doing it. There will be some reason. So this is minus 2 to the power k plus 1 minus 1. So plus 1 and minus 1 cancels out. So that is fine, right? So this entire expression that we have written now is going to be minus representative of minus b. Okay, so if you think what we have written, let me show. So this entire part, so it was a plus this entire part. This is representing how, what, minus b. So we can always write that so b prime minus 2 to the k minus 1 is equal to minus b. We can do that. So I can make it, I can simplify this, right? I can write to b to the b prime is equal to 2 to the power k minus 1 minus b, and it goes to the other side, plus 1. We can do this, right? So there is a specific reason why we have kind of formatted the sum in a particular way? Why did we come up with this 2 to the power k minus 1 plus 1 kind of a business, right? There's a reason why we have done that, and this seems very friendly to implement such things in hardware, right? So if you observe, again I'm changing the color to kind of stress on these two things. There are two parts to it. There is this part and then there is this part. Okay. So if you look at B prime and look at the first part of this expression on the RHS, 2 to the power k minus 1 minus B. If you carefully think, you will see that there is a direct relation, bit relation, like a Boolean expression that you can write directly with respect to B. Okay, I will not give out the answer, but first show you some examples. So if I have, let's say I am considering B is equal to, let's say 3, right? So if it is B is equal to 3 in a 3-bit system, it is going to be equivalent to 0, 1, 1, right? So if it is a if it is 3 bits, right? What is the value of 2 to the power k minus 1? This is going to be how much? 2 to the power 3 minus 1. This is going to be how much? 7, right? And 7 minus 3 is going to be 4. So 7 minus 3 is going to be 4. And what is the value of 4? The value of 4 is 1, 0, 0. Okay. So if B is 3 or 0, 1, 1 in a 3-bit system, the value of 2 to the power k minus 1 minus B is going to be 1, 0, 0. Let us take another example. Let us try to use a 4-bit system, and in the 4-bit system, let's say the value of, so this is 3 bits. So don't confuse the value of B with the number of bits in the system. The number of bits in the system is 3. The value of B also chosen is 3 here. Okay. So now let us look at another example. Here B is equal to, let's say 9. Okay. 9. And we are using a 4-bit system. So this is going to be equivalent to 1, 0, 0, 1. No doubt about it. Right. 1, 0, 1, 0, 0, 1 is 9. Right. What is the value of 2 to the power k minus 1? 2 to the power k minus 1 is equal to 2 to the power 4 minus 1 is equal to 15. And what is the value of 15 minus 9? Because I have to do 2 to the power k minus 1 minus b, right? 2 to the power k minus 1 minus b. So 15 minus 1, 15 minus 9 is going to be 6. In a 4-bit system, what is the value of 6? 0, 1, 1, 0. Right? So now you can start appreciating that what is the relationship between B and 2 to the power k minus 1 minus B. You can simply see that they are complements of each other. Okay. So 0, 1, 1, if you complement every bit, it becomes 1, 0, 0. If you have 9, 1, 0, 0, 1, if you complement every bit, it becomes 0, 1, 1, 0. Okay, simply, then I can write, this is a major observation, that this is nothing but B's complement. Okay. Then you add a 1. So if you look at books, they'll directly call this as a 2's complement. They'll not really get into the details of exactly why this works and so on. So now you can understand that this is a direct way to do subtraction, but before that you need to process the result, process the operands a little bit, right? So you cannot directly feed B. We have to feed, instead of B, we have to add B prime, where B prime is nothing but B complement plus 1. So effectively, instead of doing A minus B, right? Instead of doing A minus B, what we are doing is A plus B bar plus 1. Okay. So this is known as the complement. Often they will call it 1's complement. This is called 1's complement, and when you add another 1 to this 1's complement, this entire thing is called, so this is just add 1. This entire thing is called 2's complement. Okay. So 2's complement is what? For a number, this is a representation of the number, and this representation of the number is as follows. You basically complement the number and add 1. Okay. So that is how you can compute the 2's complement of any number. Right? Just invert the number and add 1. Okay. So this could be on for signed number also you can do this operation. So you can think that the most significant bit, if it is 1, this is going to be a negative number, and if the most significant bit is 0, this is going to be a positive number. And in the next lecture we can also show you some examples how to do conversions in between decimal, right? If you are given a decimal number, let's say minus 17, how do you express that in 2's complement? You can try out, or vice versa. If you are given a 2's complement number, you should be able to interpret that what is the decimal value that is being expressed, right? Because once you do this computer arithmetic, right, if the answer is negative, you will not have a direct way to interpret the answer unless and until you appreciate that this number is available in 2's complement form, and then from there extract the decimal value, right? So here we are now having an agreement that all the arithmetic computations that are going to go on inside the CPU, they can only speak in 2's complement format. And this is not a big deal for positive numbers, right? For positive numbers, it won't affect, right? You can directly, the result is going to be evident. But if it is a negative number, in case of a negative number, you have to really do a calculation to kind of gauge what is the value, decimal value or the magnitude is, right? The sign is negative, fine, but what's the magnitude is something that we need to kind of understand, right? So I'll try to do a few conversions so that you become more familiar. So now I will take a small break and try to show you the circuit of our ALU, because we will slowly start building our computer, and I would recommend you guys to start building with me, right? So that if there are any confusions, I would be able to clarify. Okay. So let me show you first that how the I'll go to circuit verse, right? I'll go to circuit verse and then show you the entire ALU. So before that, let me show you the processor, right? So this is the entire processor, and here I'll just move my cursor to in order to tell you what things are here. If you see that there is this thing, this marked in yellow, this is our register A, this is our register B, this is our register C. Okay, this is our ALU, and this is the common bus. So the dotted lines that we have here, the yellow colored now, the long line that is running from top to bottom, this is our 8-bit common bus. Okay, and then apart from this, we also have on the left hand side a program counter. This is our program counter. This is the memory where we are storing both the data as well as the program. It has stored some program. As you can see, there is some machine code that is written 1A, 3B, 3C, 4D, whatever it means, we'll come to that later. And the top part is the program, the bottom part, this 5, 3A, these are the data. Maybe we are doing some calculation with the data, right? Whatever is the program that it does, right? Then you have this MAR, which is your memory address register. As you can see, this memory address register's output is directly input to the address of the memory. Okay, and this memory address register will read from the common bus. So these are all registers, right? And we know what registers are. And then we have something called instruction register. The instruction register loads the instruction from the memory and then it executes. And on the left hand side, as you can see, this is one of the most important part, right? This is the controller of our CPU. And if you see, the output lines are very similar or very familiar, should be very familiar to you now. So these are the different controls for every component in our CPU, right? Register C in, register B out, register B in, register A out, register A in, memory address register in, instruction register out, instruction register in, memory out, memory in, program counter load, program counter out, program counter increment, and so on, right? Register ALU out on the top, right? So these are the different control lines that keep the that basically make sense out of the instruction and give appropriate controls, right? Because for every instruction, as I told you, the orchestration of how these different components turn on, turn off, or how do they read data, how do they write data is going to vary, right? And the brain behind it is the controller. So if I just reset the circuit, as you can see, it is executing some instructions. The LEDs are going to, as you can see, they are directly mapped to the control word, right? So based on what operations are getting turned on or turned off, this is directly lighting up a particular LED. Okay, it's executing the same program again and again, so the pattern is repeated, but you can very easily figure out that exactly based on what thing is taking place, based on that it is going to turn on and turn off this LED. So I can stop the simulation, and if you just give one tick at a time, right? If I just give a clock tick at a time, you will see if you give a tick, the next control word changes. If you give another tick, the control word changes. If you give another tick, the control word changes, and so on. Okay, so if you see at a certain time, in this particular instance, I have register, no, sorry, not the register, sorry, ALU out is high. So the ALU is trying to write somewhere. Probably there is an add instruction that is actually going on. The register, the ALU out is high, and register A in is also high. So the light green indicates high, the dark green indicates 0 or low. So this is very clear that in this particular part, an add instruction or a subtraction instruction is going on, and ALU is outputting to the common bus, right? So that is why it is high, and register A is getting loaded by that value. That means that the computation has been finished. The ALU is trying to put the value to the accumulator or register A. So if you now change it, then there will be something else, right? So if I change it for the next one, now you can see what is going on. It's very interesting. We stopped, right? Now probably that addition has finished. A new instruction has to be executed. So now what is going on? See, the program counter out is high because the program counter is pointing to the next instruction that is going to be executed. Now the program counter is high, output is high. So I know the address of the next instruction that is going to be executed, and MAR in is high. So memory address register is listening to the common bus, and program counter is outputting to the common bus. Okay, so if you go on the top, you can see that some data is selected, right? So probably the program counter's value in the bus, right, is probably C, I don't know. So this is what is selected. The bus contains 3. So maybe this 3C, right? So this is something that this probably we are trying to show here. And it is going to select a particular value from the memory. And after that, the memory is going to write, right? Memory is going to write to the common bus. So till now, what you have is MAR in. So if the register in of this MAR, memory address register, is high, so this is going to read from the common bus, and PC out, right? The program counter is outputting to the common bus. Okay, so note that both program counter and memory address register, they only understand 4 bits. Okay, because this is not data, this is an address. So it is only a 4-bit information, and we need to be careful about that while we kind of deal with all these things. Okay, so here if we give the next clock, and we can try seeing that what is happening, right? Instruction register in, memory out, right? So now memory is actually outputting the value, instruction register is being loaded with that value. Okay, so anyway, so we'll come to the control later, right? I gave you a kind of a overview or try to show you the system in action. So this is a thing that we are going to build step by step, or at least I'm going to show you the every details of this system, how to build this, right? A very simple computer. And we have started with the ALU first. So let us look into the ALU. So if you really click on this ALU, on top, as you can see in circuit bus, you can actually save all these individual modules. So there are all these registers, right? Memory address register is a 4-bit register, as you can see, instruction register, and so on. So one of them is the ALU, and this ALU is an 8-bit ALU. Okay, so the ALU is going to have this 8 different modules. Okay, and every module is an adder or subtractor bit. Okay, and then this is actually made of, each one of them is nothing but a full adder. Okay, so what does this full adder take? A, B, and C. You create the sum and you create the carry, and this is an enable button that we have so that we enable the output to the bus, right? So this is nothing to do with the calculation. This is simply putting the value, output value to the bus. Okay, so A, B, and C are your input A, input B, and carry in. Sum and carry is your sum and carry out. Okay, so now I would request you to implement this, right? So this is a full adder, and if you look into the ALU, so the ALU, this is the ALU. The ALU is indicated by these two inputs A and B. A and B are our inputs. ALU out is this enable, so this is going to help you write to the common bus or not, right? If ALU out is 1, then only the full adders are going to write, otherwise not. So if you do not want to write, this kind of becomes red on the right hand side. So that means that it's in our definition, this is going to be a high impedance state. It's not going to write anything. So if you enable, this is going to write. And this is our addition and subtraction selection. So if you select 0, this is going to add, otherwise it is going to subtract. Okay, so now first I have shown this. So now I'll try to go back to the slides one more time before coming back here and try to show you. So now we have understood that how ALU is going to be positioned in the processor, and the ALU is basically made of full adders in our case, and we are going to use the full adder not only for addition but also for subtraction, right? Because you have already seen that addition and subtraction are not really different. It's just that the B has to be treated accordingly, right? So if B is positive, if it is an addition, we can simply go ahead and do A plus B, right? But if you want to do A minus B, or rather you want to add negative B, right? So this is a addition, given that both A and B are positive. If you want to do A minus B, we can't do addition directly here. We have to simply express this as express the same statement as the same expression as A plus B prime plus 1. So basically convert this into the 2's complement format and add them. So this was also subtraction, right, expressed as addition. So we had to, of course, do this manipulation in this 2's complement concept came up, right? And you kind of understand how this 2's complement came up, right? So this is subtraction that we are expressing it as addition. So we can use the addition circuit, right? So now let us try to understand how to do this or get this done. So this is our full adder. Okay, so this is our full adder circuit. This is the full adder circuit. The full adder circuit has two things. One is the sum, the other one is the carry out. So we are providing A, right? We are also providing B, right? And of course, there is a carry in, right? But we don't use it typically unless and until specifically mentioned. But we just use A plus B, and carry in could be 0. Okay, and we get the sum and we get the carry out. So this is a classic case of addition, the first case. But how to use this particular circuit if I also want to leverage it for subtraction? Okay, so if I want to leverage this for subtraction, if we want to subtract, there are several things I have to change in this circuit, right? So to use it for sub, what are the things that we need to do? We cannot use B, we need to use B bar. We cannot use B, we have to use B bar. Also, I have to do an addition, add 1, right? So for adding 1 itself, I need another adder. Okay, I mean, just naively speaking, you have to do these two things, right? So one of the tricks that we can play here is simply use, let's say, a multiplexer, right, to select in between B and B bar. So I am trying to show this part of the circuit, right? So let us keep this apart, like let it be here. So here I am saying either B or B bar, right? Let us come to the addition next. But whenever I have this condition, I want to either pass B or I want to pass B bar. Suitable candidate here is using a suitable choice is using a multiplexer, right? So if I have a multiplexer, which is a taking two inputs and giving out an output, so 2 cross 1, and a select line. Okay, so the select line is going to give out this value, and we are going to input two things. One is B, the other one is simply B bar, right? So if this is B being input to the multiplexer, the other thing that we can input to the multiplexer is a B bar. Okay, so B is fed here, B bar is fed here. Okay, so this is going to be 0, this is going to be 1. I mean the selection operation. These are 1-bit select, so 0 or 1, and this is again going and being fed to one of the full adder inputs. And you can also see that if select is equal to 0, I am passing B. If select is equal to 1, I am passing B bar, which is nice, right? Then I can actually use the select bit for selecting addition or subtraction. So 0 could mean add, right? And 1 could mean subtraction. But there is one more work to do. We also have to add 1, right? So for that, we can play this trick. It's not really a trick, which is just existing input that carry in just is lying idle, right? So if I say that subtraction is going to use the value as 1 and addition is going to use the value as 0, I can simply pass this bit to carry in. So if I have A and B, if I do subtraction bit is equal to 1, which is the select line here, this is going to be 1 and this is also going to be 1. Then what is the output? The output is going to be A plus B bar plus 1, right? So if I do subtract, or the select bit is equal to 1, if this select bit is equal to 1, I basically do A plus B bar plus 1. If the select bit is equal to 0, I do A plus B, right? Or I have used capital letters here in the bottom. Yes, doesn't matter. So if I use select bit is equal to 0, this is a regular add. If I use select bit is equal to 1, this is a subtract. Okay, this is one option. The another option you can also use is instead of a multiplexer, This is just an inversion because you are here using a NOT gate as well as a multiplexer. You can also use an XOR gate, right? How to use an XOR gate? You can also use an XOR gate, because XOR gate is, if you see the expression, I want to find B complement or not find B complement, right? So if you see what is XOR, XOR is, if I want to do, let's say, B, because one of the operands that we want to manipulate is B, B XOR, let's say I want to XOR it with the select line, which is S, right? What is this expression? This expression is equal to B S complement plus B complement S is the XOR function, right? So if S is equal to 0, right? If S is equal to 0, B XOR S is equal to how much? This is going to be B, right? Because S bar, this is going to go away, and S bar is going to be 1, and B in dot 1, B and 1 is going to be B. If S is equal to 1, then B XOR S is going to be how much? This is going to be B bar, right? So it's a very nice way. So the way we have done it earlier was use this and feed it to a multiplexer, use a NOT gate and all. Here we are actually using some digital logic tricks. Okay, this is, you can call it more of a digital logic trick, right? So you can use this kind of thing. A goes as it is, don't worry about it. So maybe you just use a different color to write the circuit. So this is A, that goes to the full adder. Then B also goes to the full adder, but through this XOR gate, right? We can use an XOR gate, and this is fed to the full adder. Okay, this one is going to be your select bit. Okay, so select bit for whether you want to do addition or subtraction, and here is your full adder, FA, full adder. You have sum and you have carry out. Okay, so I'll write sum because it might be confusing. You have an S, and this is your carry in, this is carry out, and this carry in is nothing but S. Okay, so if you do this circuit, so this is going to be, if S is equal to 0, this is an addition operation, this is going to do A plus B. If it is S is equal to 1, this is going to be a subtraction operation, this is A minus B, but what really gets done is A plus B complement plus 1. Okay, so the note that the answer is going to be available in the 2's complement format. This is very important. We will show you some more examples. Okay, so now going back to our circuit, we have shown you the entire full adder, which is 8 bits, and if we zoom into the details of one of them, this is exactly whatever I have shown you. You have A, you have B, and you have C. C is the carry in, and here you can see that this is your select line, and the select line is also shorted with the carry in, right? So let me show you the select line. The select line is here. We call it AS because I call it a select line for addition or subtraction. That's why it is AS, add or subtract. If you do A is equal to 1, this is basically going to be behaving as a subtraction circuit. As you can see, light green means 1 high. So whatever is the value of A and B, this XOR gate has the lower input as high. So if I put it 0, this is low. If I put it high, it is 1. And carry in is also becoming 1. So this actually does B complement plus 1. Okay. So to a full adder, the full adder is going to receive A and B bar, and C is equal to 1. So effectively the sum is going to become A plus B bar plus 1. Okay. Hope this implementation is clear. And we are going to have a cascade of this, right? So this is the first full adder. The carry output of the first full adder goes to the carry input of the next full adder. Okay, so don't use this carry here, because this is, we are trying to do a ripple carry adder, right? Once we introduce this carry in to enable the subtraction, the carry out of this is going to go to the carry in of the next one, and it is going to continue. So it's going to continue, right? So carry out goes to the carry in of the next one, and again carry out goes to the carry in of the next one, and so on. Okay, so finally your carry, whatever is going, so this carry out is again going to the carry in of the last one, and the final carry out is the result is going to be stored as in the status register. So as you can see, I have these 4 flags, right? One is the carry flag, one is the not carry flag, one is the not 0 flag, and one is the 0 flag. If your result is 0, as you can see, the sum here is for some reason it is 0. So the 0 flag is set, right? ZF is set. Okay. So you can try out something very simple. Let's say I want to add 2 numbers, right? So let us restrict ourselves to 4 bits, right? So that we can understand what is going on. So let me try adding, let's say 9, 1, 0, 0. So you can see here what is the value. Okay. So this becomes 9. 1, 0, 0, 1 is 9. A is 9. And let's say B is equal to 3. So 0, 0, 1, 1, 3. And what is the value of 9 plus 3? The 9 plus 3 is going, if I put A is equal to 0, so 9 plus 3 is going to be 12, right? 1, 1, 0, 0, and so in hexadecimal notation, this is going to be C, right? This is correct. If I want to make A is equal to 1, the value is going to be 6, right? So if I put A is equal to 1, I have just done, there's no black magic, nothing hidden here, right? Everything has been showed how this exactly the subtraction operation works, including the circuit, and how do we integrate the subtraction operation on a regular full adder using that XOR gate. So 9 minus 3 is 6, and if I activate A is equal to 1, which is the control input for operation selection of the ALU, this becomes 6. Okay, and you can try out more examples. Let's say I want to have this is D, right, which is I think 13. So if I want to add, let's say 13 and let's say I want to add 13 and 12, right? So 13 and 12 is 25. Okay, so if I do a subtraction, you can see the it becomes 13 minus 12. This is 1 because AS is equal to 1 here. Okay, if I make it addition, it becomes 19, but 19 is in a hexadecimal format. So 19 is 9 into 16 to the power 0, right, plus 1 into 16 to the power 1. So 16 plus 9, which is 25. So it's correct. Okay, here also you can verify. So this is 1 is 16 and 1001 is 9. So 16, 9, this is going to be 25. Okay, you can play with this. So you can also try to interpret this. If the answer is negative, you can simply try out one. I can try out something very simple. Let's say I have 7, right? This is 7. So 7 minus 12, this is going to be how much? This is going to be, so this is, just a minute, this is 0. So this is an addition. So 7 plus 12 is 19. So this is 16 plus 3, 19, fine, right? So if I try to do a subtraction, the subtraction should give us minus 5, right? 7 minus 12 is minus 5. But you get this big answer. Okay, so FB, right? Whatever this means, this is your answer. Now the thing is that you have to convert this into the regular format in order to interpret it. This is actually 2's complement format. I'll show you how to do it in the next lecture. Here you have to keep this 1 as it is. You have to start from the left hand side, right hand side, the least significant bit, which is 1. Then keep, once you encounter a 1, you keep on flipping those bits, right? So this 1 will become 0, this will become 1, this will all become zeros. effectively answer is going to be all zeros, 1, 0, 1. Okay, so which is basically -5. There is a, you can always find it yourself how to go from a 2's complement format to the regular signed magnitude form. You can try doing it. You are just, I mean, this recipe is there in the book, but why it works is more important to be understood. So I will try to discuss it in the next lecture. But this is what, right? I can show you, this is our ALU, and the ALU is going to work in this way. So you have to all select a particular operation. So either you want to find addition result or you want to find subtraction result. This is one control, one input to the ALU, and the other input to the ALU is whether you want the result to be written to the bus or not. Because if the ALU continuously outputs to the bus, you cannot do any other register transfer operations, the memory cannot write, right? So this is going to create a bus conflict. You need to make sure that the ALU is not outputting when it is not required. So this ALU out should generally be 0, so that it doesn't disturb the bus, right? See, this is undefined, which means that ALU is not outputting anything. Okay, and of course you need these two inputs A and B, which are two 8-bit numbers, and this is directly read from two registers, register A and register B. Okay, so I will stop the session here, right? In the next session, we are going to look at a little bit into how to do binary arithmetic with this 2's complement and interpret that so that you have a working knowledge. And after that, we are going to move straight forward towards the orchestration of running a computer program, right? We have understood how an assembly level program is run, right? Or at least what to make sense out of the assembly level program. I gave you one exercise. We had a loop, right? And I wanted you to convert that loop into an assembly level instruction and set of assembly level instructions or a sequence, right? And set is not the right word. Sequence of instructions, because the sequence matters, not really what instruction. If you perturb the sequence of the instruction, this is going to result in a different program and unexpected output, right? So it's very important to have the sequence properly ordered. Okay, so you understand what this instruction means. You understand how to encode an instruction in our instruction set architecture. We have a specific format. The top 4 bits indicate the operation that we are going to execute. The last 4 bits is going to indicate either an address, if you are trying to refer to an address and load those data in the registers, or it is going to refer to an immediate value, which is again unfortunately 4 bits, because I do not have any more bits to accommodate in our instructions format. It's 8 bits, right? So it's only the immediate instructions can go up to the immediate value can go up to 15, right? 0 to 15. Okay, so that is all. And then we also looked into the ALU now, so you know kind of how subtraction works. So we are going to restrict ourselves to this. If you had logical operations on top of this, right? Suppose you had and not, as we discussed, right? So in that case, what will happen is this AS, right, is going to be 2 bits, right? Not a single bit. And this is going to go to a decoder. Okay, so this decoder is going to see if it is 0 or 1, assuming that add is 0, 0 and subtraction is 0, 1. It is always going to select the full adder unit. And within the full adder, it is going to look at the least significant bit, right? And or if it is 1, not 0, if it is 1, it is going to trigger subtraction. If it is 0, it is not going to trigger subtraction. If it is, let's say, 0, 0 and 0, 1 is gone for addition subtraction. Now comes 1, 0. If it is 1, 0, it is the decoder's out. The third output is go to a AND circuit, which basically takes again A and B, finds out the AND of them, and instead of sum, you have an AND output. Similarly, if it is 1, 1, instead of taking A and B, it is just going to take A, let's say, and find out the complement of A, and the output is a NOT of A. Okay. And you can of course have enables. The enable is common, right? The enable is basically the ALU's enable, not really the full adder's enable. So this the ALU out could be and enable signal for all the outputs, right? You can do it in common together. Okay, so that will be it, right? So this is the implementation of the ALU. We will try out some more examples in the next session, and after that, in the last week, primarily we are going to see how the control works in more details in terms of an implementation perspective, and how to basically build the control system, right? There are things like hardware control, software control, and so on. We are going to look into how to implement them and make sure that you understand all the implementation details of this computer and appreciate it as it executes a code, right? uh, okay, I will keep it till here.